And next we have Peter Melchior, who is an assistant professor at Princeton, working really in a multidisciplinary space. So he's both in the astronomy department, but also the statistics and machine learning department, thinking about how can we maximally embed physics in machine learning models in a way that doesn't make them too restrictive.
Excellent. Thanks very much. So since I'm the last speaker and I have had great kind of speakers to set up the stage for me, I can answer a question how we can combine physics and machine learning in ways that may go beyond what has been discussed today, but also may provide an alternative to what we've been sometimes forced to do, namely to just adopt a machine learning architecture because it's the and best trained thing that comes out of industry. So let's see what we can do. My name is Peter Melchior. I lead the Astro Data Lab at Princeton. And kind of our main interest is to take the data that exist, the vast amounts of data that are being generated and continue to be generated, and infer something about the universe from that. And given what we've just heard from François, for instance, about the fact that it's now much easier than it used to be to utilize these large data sets, so thank you very much, it is much easier. And given the the state of AI as being something that has shown tremendous and very interesting solutions and found ways to deal with data in ways that we've never seen before, that begs the question, why isn't astrophysics solved? Any guesses? I have a few ideas of my own. So let's look at one of the remarkable things that have happened a couple of years ago, right? ChatGPT came along and allowed to do things like this. And you prompt it, obviously, you know all this, but the answer here is actually interesting, right? Because either it remembered that joke because it has seen it before, or it came up with something creatively on its own. And in some cases, we have seen actual creative or seemingly creative things from these systems, and they are interesting and remarkable. But then this also is ChatGPT. I give you a little bit of time to spot this. All right, so this doesn't look bad, right? So if you look at it, this goes correctly for quite a while, and then it doesn't. And it's interesting because apparently it understands some aspect of arithmetic, but not all of it. It's learned some of it, so some of it was represented often enough in its training data that it figured it out, because it's close, right? This is astonishingly close for random guessing. This would be impossible. So it has figured something out, but not everything. And you can see this actually, I think the best example of this is when you let ChatGPT or the large language models play chess. These games are played on a text description of chess, and so you can see that it moves things, but it moves them, so it starts off really good, and then it starts doing interesting things. And the longer this goes, the more bizarre the game gets. Right? And what that tells us is that it has the ability to memorize openings really well, and then it starts playing like a 5-year-old. Basically, it eats its pieces and does things like it brings pieces back that were captured. It does moves that are illegal, like this one, and just keeps on doing this. This one's. So what does that mean? Right? This appears to us like this is immediately obvious to us when you have played chess. You understand that a lot of these moves break the rules of chess. Right? And that means that in its training data, it has recognized some aspect of the rule set, but not all of it. Yeah, it keeps on going, like it's amazing. So it has figured out something, but not all of it. And that begs the question, can we improve upon that, and how would we do this? So a better approach, if you think about what AI does in this the space of physics and the physical sciences, this is a really good example of and don't take my word for it, the Nobel Prize thought, the Nobel Committee thought that's a good example. And so there is the prediction of three-dimensional molecular structure on the basis of text is a problem that has not been solved convincingly by decades of fundamental research. And then kind of DeepMind came along and did this, and basically obliterated the existing solutions. But look at this. This is a complicated architecture. There's some stuff that happens here. There's some database search. There's kind of a clever way. This part here is a very clever way of doing a search. Right? And then here's a bit that says structure module, and there's some clever things in here. But for instance, in here, there's an invariant representation. So these molecules are invariant under rotation. So they realize that this structure molecule needs to have that invariance sort of baked into it. There's some very clever reasoning and some very, very kind of high-level engineering and a lot of work that went into this in order to make this work. But it is highly structured. That's the main point. This is not just one kind of gigantic model. They are it's broken down, and every part has its own responsibilities. That's an interesting takeaway, and that kind of will be sort of the highlight or kind of the summary of what I'm presenting. And there's something that we haven't really talked about here. This is kind of a machine learning meeting in a physical context. And the way that we think about physics is by thinking about relations between causes and effects. That's how the laws are expressed. That's what they do. That's what they describe. And the fact that we can describe a lot of the world this way makes physics so powerful. So if you look at what machine learning regularly does, is that you have some functional form that you kind of have a mapping between some two spaces, and you have data on both of these sides, and you train this in one form or another. Supervised, self-supervised, unsupervised, you name it, but it basically operates in this space. And the mantra is that with enough data, anything can be learned. On the other hand, right, we have the universal, or ideally universal laws of nature, and then we reason about them, and we find very, very concise models with very few parameters that are incredibly capable of explaining a range of outcomes. It's a very, very different styles of representing the world. So let me kind of give you kind of a more sort of a direct example. So imagine that you run a self-driving car company, right? And then you have sensors in your cars that says whether it rains or not. And then what it finds is that, well, if it rains, then the braking takes longer. So that's a very simple relation, a correlation, if you will, between sensors that kind of measure whether it rains, some kind of windshield sensor or something like that, and something about the acceleration sensors in your car. And you can correlate them, and all is good. But let's imagine that kind of you develop your car in California where it never rains, and then you end up in a place where it actually might start to rain, and ask the question, how do you have to modify your model in order to account for that? And then with a physics mindset, you would say, well, that's probably a good idea. To say that, well, when it rains, what actually happens is that the friction coefficient is reduced, and I can just compute the braking distance of the car once I know that. Right. So if you think about an observational setting, I would even go one further. Because I can make this relation here very simple, I can actually start to invert this relation, which is what we do in experimental and specifically in observational settings. We observe something about kind of, in this case, the driving of cars, and then we reduce something, we find out something, in this case about the state of the atmosphere. So if I were kind of to make an experiment with 1 million self-driving cars, you can ask the question, what is the state of the atmosphere on the basis of their acceleration sensors? Can I do that? And if I can, then I have sort of, this is an example of how kind of to turn some environmental or other sensors into a physics experiment. Right. So that's what I want to do in the end, right? We have tons of data on various things, but there are aspects of it that I do not understand. In this case, that would be, in this example, the state of the atmosphere. So let me give you a bunch of examples on how we actually do this in practice and what it is, what it can do in an astrophysical setting. This is a segment of the sky observed with HSC, the same images that François just spoke about. They're beautiful, they're very detailed, and they're also very messy, right? There are so many galaxies, and they're kind of, it's really kind of very bountiful. It's a very rich data set, but it's not easy to deal with. So if I want to model this, I have to make a couple of modeling assumptions. So the modeling assumptions that in my group we make is that I'm describing this image as a hyperspectral data cube. So there's kind of 2 dimensions in pixels and 1 dimension in this kind of vertical direction. In this case, think of this as the wavelength axis. So it changes the wavelength are in this axis. And every object here is described, it has a spectrum and it has a morphology. I don't have to say anything about what defines the spectrum and what defines the morphology. Let's just imagine that they're freeform, just a bunch of vectors and numbers. But what I have to account for, and François spoke about that as well, is that if I observe this object, then I have to account for the fact that this model of the sky is not what I'm going to get. Through my telescope and through the atmosphere, there are effects like this. There's some convolution that happens in the atmosphere and in the optics. There's some detector that will pixelate this, and then obviously the entire thing is noisy. I know all of these operations. I don't need a neural network to figure out what those operations are. I know them. They can be analytically described. And you can see this in classical signal processing. This is what's called a forward operator, and that is what it describes. That's what it does. And then the noise, for instance, that is captured analytically by a probabilistic model. In this case, we assume Gaussian noise, so you get this quadratic loss function that you're fitting. That's how these pieces are explicitly modeled. So think about this again, right? In the same way I just walked you from it rains to the braking distance of cars. These are probabilistic models that express the causal relationship between different entities. So here we have the amplitude, here we have the shape that gives rise to the image as it would be seen in an ideal condition of a single source here, a single galaxy. Then I have k of these, I sum them up, that's my vector, that's my representation of the sky. And then I have this convolution operator, or this rendering operator that gives me the data. I don't have to this thing here, I know it's incredibly well measured. This is what surveys invest heavily in. There is a notion of how these work. So that means that the causal nature in this here has to do with the fact that I know precisely that the atmosphere and the optics cause this blurring. I don't need to model this. I can impose it. But it's caused by something I understand and can control. It might be caused by something else that I don't understand, and then I have to model it explicitly. But in this case, I know what it does. And I know it is causing it. And this is the cause-effect relationship that is important to recognize in a lot of these problems. All right. So if we fit this, we get, this is here the model. These are the residuals of the model. That all looks great. Sorry, going back. And you can see that there's some interlopers here which have to do and they're not part of this galaxy number 19. They're sort of separate from it. And that's what you expect, but it's a very good model. If we do this with multiple observations, and this is where I think François' approach, or what Alex said earlier today, differs from what I'm doing here, is that I have different forward operators, these PLs. For every observation L, I have a different forward operator because I know what the difference is between the model on the sky that I have posited and what I'm going to see in my observations. I don't have to guess. I don't have to do some contrastive alignment. I don't need to do any of these things because I know what it is. There's a causal relationship behind these things. And this means that I can make one model that explains this blurry ground-based image from HSC and this not blurry space-based image from HST, from the Hubble Space Telescope. You can see there's also difference here. Here we have multiple colors. Here I don't. But both of these can be explained by the underlying model. Here is actually the underlying model in the same colors as here. And if you look very closely, right, this looks good. I didn't have to make any assumptions. I causally said that there is a relation, there's a reason why these things look different, and I can explain exactly what that reason is. This is why my model, which I'm going to use a neural network for in order to describe these guys, doesn't have to deal with it. Right. So what do we, oops, sorry, one more. What we're going to do is we are now going to assume that I have a prior distribution of galaxy images, of models how a galaxy image can look like. I know that Alex is here. He's done very similar things. We are going to use a diffusion model for that prior. And so what you see in this graphical model is that this thing is not an unknown anymore. It's derived from this distribution of shapes. This is how a galaxy image can look like. And then we're going to kind of optimize it jointly, kind of going for the maximum posterior solution or posterior samples of that distribution, and everything is good. Right, so here's the gradients of that. The gradients here that arise here in optimization, they lend themselves to be mapped really well to diffusion models, and now we can express the shape of galaxies by learning how to denoise images like this into galaxy images like that. Things that look like galaxies, which are kind of there. So if they have a peak in the center, they have some structure around it, maybe there's some spiral structure around it, that can very effectively learn by having examples of that, making them noisy, and then learning how to denoise them again. That's how you learn these things. So if we do this, here's an example between kind of the old version of the code that didn't use neural networks and the new version of the code that does. And you can see that kind of in this model here, you can see features. We call them spider webs, things like this that don't look real. They're not quite important enough. You can't see in the residuals. They're all flat. So it's kind of at the noise level, but it's not quite right. And so here these neural networks have learned kind of that galaxies are smooth. They are kind of more extended. They have like regular features. And this is what they have learned. Right. Whoop. This clicker is a little slow. Right. So can we go beyond that? Now you ask the question, okay, I've imposed a prior. You have to ask whenever someone does that, you have to ask the question, how do you know your prior? Where does it come from? And in the past, one had to say, well, I assumed something. Now there's a set of works from last year over here that express this as a hierarchical problem. So we can ask the question, what does my prior need to be? Like, how can I adjust my prior in order to give the right sort of distributional properties for this thing? So what are the parameters of my prior, if you will, the hyperparameters of the problem, in order for a prior for the shapes of galaxies to make any sense to look like the data? And you can learn that prior by backpropagating the data down here onto these parameters. Really, this clicker is too slow. All right. So what happens here is that we assumed some prior that we had here. This is sort of the version 1 of the prior. Here is kind of the observation. Here are the residuals, and you see there are structures in the residuals. This is not, like, we didn't run this just on one galaxy. We ran this on something like 1 million galaxies, and all of them have, like, structured residuals. If you backpropagate the collection, the entire ensemble of these residuals, you can sort of sense that there needs to be changes, or there should be changes to the prior that would make these residuals vanish, or at least become smaller. And so if you backpropagate this is the first run of backpropagation, where you can see quite noticeable changes. You can see these kind of knots, these patchy features that are associated with star-forming regions in the galaxy. They start to immediately emerge. We keep on doing this for kind of 10 more steps in order to make it finer and finer, but you can see the main effects already in the first iteration, the improvement that happens here. So the main takeaway from this is, by having a model that contains causal elements, namely the blurring of the atmosphere and what the detectors do and all of that, like all of the nonsense that no one actually cares about really, if we can use that and assume that, impose that, and then learn from the data what we do not know, namely the distribution of sort of galaxy shapes, how galaxies really look like. We can learn it directly from our data. So that's kind of the equivalent of taking a bunch of acceleration sensors and learning the state of the atmosphere. That's the same idea. Right? We backpropagate that, and that works because I imposed additional stability in my problem and make this prior only do galaxy shapes rather than kind of other elements like the blurring of the atmosphere. We can do this also with dust in our galaxies. So galaxies have dust. This reddening that you see here is because there is dust embedded and that obscures part of the light from background galaxies. So in here, we made a similar assumption. We need a model. So we kind of have, this was our original model. We now added a model that contains the attenuation, as it's called, basically the dimming of light when it goes through a dust, an amount of dust. And we need kind of model components for this. So here's our galaxy image that we have modeled. We have a shape, we have a spectrum. We need the same thing here. We need a shape and a spectrum. But we imposed something in addition. If we were to try to solve this, this is super high dimensional. I mean, this is highly degenerate, right? There are kind of now 4 factors that are sort of factored. There's a product of 4 factors that is super degenerate to solve. But there is structure in this problem as well. And the structure comes from the fact that the stars in here, this galaxy image here is effectively the image of the starlight of stars in the galaxy. The stars are the mechanism by which the dust is produced, which means they're causally responsible for the existence of the dust in the first place. That means that there ought to be a relation between that distribution and that distribution. And so what we expressed here is to say that instead of having one diffusion model for this thing, we now need two diffusion models, but the second one is conditional. So this distribution is the distribution of the dust given the distribution of the host galaxy light. And so this distribution is then also expressed, and it's very efficiently expressed, by a very, very small diffusion model. This diffusion model is trained on only 600 simulations we've had. Like, it's a tiny number for a diffusion model. And it turns out that the only thing we needed to recognize is the relation between the amplitude and the patchiness of the dust, given that I already have a pretty good image of the host distribution. And the reason this works is because there is a very strong relationship between these. The stars produce the dust, hence there is the relationship. There are mechanisms that dust is also destroyed, and there are other mechanisms, but the primary driver here is the fact that stars are generating at the sources of the dust to begin with. So if you assume that, you can actually fit this very highly degenerate model, you can actually fit this. So you can get here, you can see this. The redder parts is the stuff that we are now going after, and what you can see is here, these are dust maps produced from ground-based 3-band, 4-band images, and that is sort of unheard of. This hasn't been done before because you need way more data typically in order to solve a problem like this. This has been done in cases when you have complete hyperspectral imaging or 30-band imaging. We are doing this with 4-band, and we are doing this at cosmological distances where the data is way noisier than you normally have. The only reason this works is because these priors are good, and we learn them very effectively. Okay, so what about spectra? Different modality, same story. So what happens in galaxy spectra is that there are two different degrees of freedom, if you will. There's number one, there's a degree of freedom that has to do with the fact that if I change the redshift of this object, then all of these features, they just move towards the red, hence the name redshift. But there's also this effect here, that is, if you think about galaxies having what's often called a spectral type, then the type of features that arise in the spectrum, they are different. And what I do know very well is what redshifting does, because there's a mathematical equation that we believe to be true. We believe in all of our heart and mind, we believe that equation to be known and true. That means I do not have to explain this by means of a neural network. It's just not necessary. However, this part here, we do not know, and this is why we for things like spectra, we have a lot of uncertainty about what is a good generative model for spectra that you can address with, say, a foundation model approach. You can go after those this way, but you can also do it with a significantly smaller architectural choice. So let me show you. So this is a different idea. This is a different way of representing this. Here's the redshift as an input. Here's a latent variable indicating the type. We decode this into a spectrum, which an astronomer would call a rest frame. This is at redshift 0. So this is how we would, how this spectrum would appear if it were right here. But then there's cosmological expansion. That means that the redshift is caused by the stretch of all of the wavelengths due to cosmic expansions. And I can express this explicitly. I can also express, again, what sort of the sampling of the detector will do to the data. And then I get a reconstruction. And that reconstruction should better look like the data I can collect. So the only thing I need to do in order to make this sort of fully self-supervised and actually technically unsupervised is I need to have an encoder that can take in a spectrum over here and compress it into these latent variables, despite the fact that it's observed at different redshifts. So there's an attention element that allows to have some flexibility in the translational sense so that the features can arise wherever they want, as long as they are there. And so what you get here is a very, very simple, very low-dimensional representation of a generative model of galaxy spectra. And it does really well. It describes these features, including ones that it hasn't seen. So here this line is not actually observed. The black stuff is observed. The red stuff is the model. And it's missing because it's a little bit too blue for the detector to observe. But it predicts it because it has seen the same line appear in other spectra at a slightly higher redshift where it can be observed. It's very stable, and this entire thing has internally 6 parameters. So the latent space is 6-dimensional. That's it. We could do it with 2 if it weren't for active galaxies, but it's an incredibly aggressive compression. But it's also really good and useful compression. You can do, if you retrain that latent space, if you retrain the decoder, you can do super resolution similar to what Francois just showed. But again, we assume that we understand what super resolution does in this case, and that there is sort of a broadening effect that the actual detector does. Again, we assume that we sort of causally understand that. And the latent space is really useful. I think so all of these, like anything in deep learning recently deals with the fact that these latent representation or these representations that are being learned are incredibly useful for a number of things. And then you might want to sort of combine multiple representations and multimodal learning and to make them even more useful. But what this shows here is that these latent spaces are actually really meaningful. There's physical parameters associated to it. And so you can do things like the k-nearest neighbor search in order to identify what the properties in a certain location in latent space are from a few labels that you may have. So this, what you can also do is use a normalizing flow in this latent space in order to describe the entire distribution of that latent space, and then ask questions, what is if some complicated spectrum that has like 5,000 elements, is that usual or is that unusual? And I can ask the questions, what are the unusual ones, because they often drive new hypotheses. So what we've done here is doing that. We've just asked, we've embedded the DESI spectra. We've asked the questions for every one of these spectra, which are the ones that have really low probability under the distributional, under the flow that we've just modeled. And that means that we can now ask in a completely unsupervised fashion, we can ask questions like, what are the outliers in the data set? And again, right, this is an incredibly compact representation. The model is very small. The representation, the latent space is incredibly small. And yet, this works exactly in similar ways as significantly more complex architectures. So you can do more than this. So this is a more recent work. We're doing the same thing again. However, this is now done on quasars. So quasars are very powerful light sources that you can observe out to very large distances in the universe. And one of the reasons you might want to do this is because along every one of these sight lines, there could be neutral hydrogen that absorbs the light of that quasar and tells us something. Basically, it shines a light at the back. And from observing that light come to us, we can see how many of these intervening neutral hydrogen clouds there were. And that tells us something about the reionization of the universe and how galaxies change the makeup of the universe. So what does that have to do with causal reasoning? Well, again, the hydrogen cloud causes the absorption. I can try to model this, but I can also do something really, really stupid and simple and say, well, I know that absorption is always negative, so I can fit the entire data with all of the absorption in it, which gives me a biased version of how the quasar looks like, and it underestimates how much attenuation really happened, because it's sort of a mix of attenuated and unattenuated light. But what I can do is say, whenever my model that I have just built, whenever there's a dip in the data that goes below that model, that's probably caused by an intervening dust cloud, I'll just mask that out. And I keep on doing this, and what happens is that you iterate this a bunch of times, and what it does is it elevates the entire luminosity of the background quasar and gives me a much clearer picture of where those intervening clouds are. And so you can keep on refining this. We have done that here in this paper, and it's a little hard to see, but our model is this red line, and if you go over here, you can see it a little bit. The data is down here, because you have these dips, that's called a Lyman alpha forest. You have these dips where it's suppressed. And you can see our model comes up significantly over this, specifically on the left side here. And the only thing we've done is to say, well, I know that absorption is absorbing light. I'm just filtering the parts out that I believe to be absorbent. There's something that's absorbing the light of the background, and then refitting that again. I'm not imposing any knowledge of these places. I'm actually removing information because I feel that it would have been contaminated. That works totally fine. And lastly, And that's actually the most accurate model for what's called the quasi-continuum, and therefore also the most accurate model for the Lyman alpha forest that we can make these days. And then lastly, kind of bring a bunch of these things together. Here's again the same idea, spectrum autoencoder, but now this spectrum comes from an exoplanet, or actually rather it comes from a star that might host an exoplanet. And the orbit of the exoplanet, what it does is it pulls the star up towards us and away from us, and it gives us redshift and blueshift, the same operation, mathematically exactly the same expression that we had for the cosmological expansion, also applies to this kind of gravitational Doppler effect. So what we can do is use the same architecture and compress the spectrum and kind of deal with this redshifting and blue shifting that comes from an orbiting planet, deal with this, again, analytically. We know precisely what it is. And that means that we can do two things at the same time. We can say there is a turbulent stellar atmosphere over here. So it does a bunch of things, and it means that parts of the atmosphere is moving, and that movement obscures, it sort of mimics the effects of an exoplanet. There's so much movement on the surface of a star that it completely dominates over the gravitational pull of the planet. So the signal is completely swamped. But I can now do the same thing. We're using an autoencoder again. Here's an encoder. Here's our latent space. Here's a decoder, and doing this again. But we have this secondary path. We take this spectrum. What happens is that there's kind of a baseline. We just take the first epoch, define it as a baseline, and then only look at the changes with respect to that baseline. That baseline is changing for two reasons. First, the stellar atmosphere is changing. That's this path here. And second, there's a planet that pulls on it, and depending, like when time advances, the pull is slightly different. So these two paths are independent from each other, but we can estimate both of them at the same time because we know precisely what the Doppler shift will do to the spectrum. The Doppler shift in this case is tiny. You can only really see it if you observe many, many thousands of kind of spectral elements. Kind of the spectrum is really, really fine and resolved. However, this looks completely degenerate. It looks technically impossible, and yet we can make this work. And the reason for doing this is kind of the strength here of the kind of the causal assumptions of the Doppler shift and how it acts. I can show you kind of more details. We will also actually go beyond that and even describe the time evolution if you're interested in neural ODEs, so time evolutions, and modeling and dynamical systems. I'm happy to talk offline. I don't have the time for this. But we are kind of even going beyond that by assuming that kind of the evolution on the surface of a star has its own kind of timescales and its own kind of temporal signatures that we can capture. And ultimately, what we want to do is go after kind of Earth analogs for which you really have to suppress the noise of these various contributions. And what we are doing is we are going to make kind of causal assumptions about all of the things that happen to our signal. Right. So lastly, let me just summarize. If you get AI off the shelf, what you're getting is some really interesting, capable representation, but the lack of really kind of strict obedience to rules that we believe to be important and potentially kind of critical for the solutions of this. And then on the other hand, right, what I just proposed is actually not too different from what people have done before. So if you think about this, right, what we normally see under the term of kind of structured learning is some form of very strong inductive bias. So a CNN has translational invariance. So for image and computer vision problems, you often do CNNs because they have the right type of structure. And what that does, it reduces the search space for the solutions that you might want to find. It reduces the requirements on data and kind of training and the amount of training, and it gives you these meaningful representations. So where I would like to go beyond, and I think what we in kind of the physics community in the physical sciences have an opportunity to do is to say, well, we've understood a fair bit about the problem already. We might as well just bake it in. If there's a way to differentiate through the equations that we've already understood to be true, we can identify the parts that are not actually known and learn those. And that's what I'm kind of in here for. This is the stuff where that I find exciting, is to learn the parts that are not already captured by existing theory. And so in a causal sense, right, what it does is it creates responsibility for the model components. They're not arbitrary anymore. They're causes and their effects and their transformations in between. That breaks a lot of the sort of the risk for cheating that happens in kind of deep architectures that find bypasses that are not legal under our understanding of the rules of the game. And so what that allows you to do is to do kind of some interrogation of the components that you have just learned, because they're much smaller, like literally much smaller. The neural network is much smaller, the representation is much smaller. But the main point is it also has a smaller task to do. It's much clearer what it's supposed to be doing. And so you can do things like adversarial attacks on that part, or kind of try to see when this kind of your neural network is not hallucinating, and kind of I give you a bunch of examples where we have done that. But the main point is that we knew much more so what we are doing because the representation is much simpler of the data-driven component of this more general hybrid system. And you can see the structuring now appearing in other cases, like DeepSeek does the mixture of experts. There's the previous tool Former, which is kind of a similar idea where kind of some rules are sort of baked into the use of the tools. And then there's some kind of hierarchical or superstructure that identifies which of the tools that need to be used. That's very similar to this, right? So you can see that this type of structure also makes it into AI research. And I would argue that's going to continue to happen. Whenever AI hits the real world, there are laws in that real world that are expressed typically by the laws of physics. And so if you fly a drone, then it needs to obey the thing that there's sort of gravity in their winds. And the rules by which these are described are kind of typically expressed by the laws of physics. So it would be good if you combine them at some fundamental level. And that's what I'm arguing here, that it actually allows us to go beyond the state where we are right now by imposing structure we already know to be important. So I'll end here and acknowledge the people who are working with me on this and also our funding. Thank you very much.
Thank you, Peter. Any questions? Is there a raised hand?
Very much agree. What about discovering causality?
Really good question. It's good that you bring this up because there's often sort of a confusion of these two terms, right? So what I showed you here is imposing causal structure in order to kind of simplify the problem and kind of reduce the search space and all of these things. That's different from causal inference. And causal inference is, if you look at the ways that this is done, is effectively kind of a glorious sort of tree search over kind of the different options of confounding factors and kind of could this have happened versus this. And I'd argue that we have the benefit of like physical understanding in many of the spaces, so we don't have to do this. I'm not arguing that you don't want to do hypothesis testing with models that you haven't built, but it's the full discovery of the entire kind of hypothesis space, I think, is something I feel is, well, at least very difficult. So this one doesn't require, what I showed is imposing the causal structure rather than trying to infer it.
So you mentioned that you can encode in extremely low dimensions. Mm-hmm. I think it was even 2 with this not active. Have you tried to study what those are?
Yeah, like I can go back, but it's been actually known for quite a while, I think since the late 90s. So the 2 dominant dimensions for galaxy spectra are stellar mass and star formation rate. So kind of how massive is it and how kind of quickly does it form stars right now or over the sort of recent past. And that's what you get to see. And our latent space is primarily structured this way as well. I can go back to the slides, but that's kind of the 2 main ones. The other ones that you get to see here are, let me go there. This one here. So what you see is star formation rate is actually this. So old stellar populations here, very young stellar populations there. So these are the star-bursty galaxies. And then mass is the green stuff up there is mass. So that was known. But we immediately find other things like this one here. This is dust attenuation. So how reddened is that spectrum? And it's kind of not so easily sort of over here. It's sort of concentrated in the middle part. And then you have things like redshift you can see on this outer edge, for instance. So there's more dimensions that we're pressing in this kind of 2-dimensional UMAP representation here. So this is UMAP representing kind of 6-dimensional space. But the primary ones are this one and this one.
Yeah, thanks for a nice talk. I mean, that's really the crux of the issue. So do you need all the structure, or can you just throw data at it? And so, I mean, and then you mentioned at the end, so, as long as you can differentiate it through it, and so you can have like some nice hierarchical system, it's all differentiable. And one of the things that you observe also in like graph neural networks and so on is that the structure might then also kind of be a obstacle for optimization, so like over-parameterization and so on, and then, graph neural networks are theoretically nice, but then they're over-smooth and these things. So do you have a sense in the astrophysical case, so kind of between make differentiable physics and build in like all the inductive bias that we know versus kind of build like some self-supervised foundation model, like where things stand?
Yeah, so there's really interesting kind of research that happens on whether you're better off fitting a very, very flexible model and basically just have it sorted out, and that depends on whether you have enough data and compute in order to sort of pull this off, or whether you're kind of imposing structure. But one of the, that's kind of empirical evidence from something that my group has done, but also others have found similar things, is that if you put in very strict requirements to the kind of solutions that you want, so for instance, imposing kind of a certain invariance at the level of the loss function by penalizing the non-invariant race of this, then the optimizer just won't find it. It just kind of fails. It sits at some suboptimal place and nothing ever happens, and no amount of data would help you. And so if you're in this case where kind of gobs of data, like heaps of data are available, it is better to remove the restrictions and have sort of find a path to kind of good solutions, and maybe potentially impose like extra requirements at the end, or just accept the fact that sort of an invariance is only approximate and not quite exact. But it's a question of how much data and compute you can throw at the problem in order to sort of establish something you believe to be true without enforcing it. But what is certainly true is if you enforce it too hard, like for instance pins do, when you like really write down the equations, and it can only do this thing, and then you give it some data, and then you hope that it finds a solution, that you often find that training to be very, very brittle.
Hello, thank you for the talk. So if I put a structure in the model, am I restricted to get results that follow that structure? For example, if my structure is standard model, and can I get results that might give me something, tell me about beyond standard model?
Right, yeah, good question. So one way you can think about this is you kind of use in your forward path, you use sort of whatever your sort of standard model predicts, and then you allow a kind of deviation, say a residual model to exist, and you capture what that residual model is doing. Now the question that you have to ask, and there's no kind of one solution that will kind of always work in this case. I think in all of these you have to sort of ask the question, what do you know or what do you believe to know, and how strongly do you want to impose that knowledge? So one of the main questions if you sort of blend like a residual model with the previous model is, can the residual model just basically wipe out everything you've done in your sort of baseline model? And then you haven't gained anything from the existence of the baseline model, and you're basically back to completely data-driven. So what I would argue is that you should be very careful about kind of what space you open up with the residual model. And maybe, for instance, you can try to, by means of the loss function, you can try to make it orthogonal. So you give it sort of a new dimension it can be explored, but it can't touch the sort of certain dimensions or certain aspects of the problem. And so that you can see whether it wants to leak out and go into that space. But you need to be careful of how you blend them so that it's not the new model is basically just erasing everything your baseline model has done, and then you basically start from scratch again.
In your just before your super resolution slide, you showed a graph that had an observed and an unobserved part. Mm-hmm. And you said like the model shows you that unobserved peak because it is observed in other samples with like higher redshift. Mm-hmm. But how accurate is the reconstruction of the spectra? Like, what's the error margin? Mm-hmm. Because it's not a smooth peak and there are irregularities.
Yeah, so a really good question. So there's there's sort of two types of errors that could be happening to a predictive model of that kind. First is the data you're encoding has noise on it and has sort of erratic structure potentially on it. And that could sort of push the encoding into a place where it doesn't need or shouldn't be ideally. And then there's the other part where whether given the encoding, the reconstruction of it would actually be accurately describing the model that you kind of have. So model is sort of model misspecification. So the model doesn't actually capture the truth realistically. And the other one is the uncertainty that propagates from the kind of the noise and sort of the peculiar features of the data that you have at test time. And both can occur. In this case, we actually checked that this is working. So there are spectra of the same source at this, which I haven't kind of plotted over here. But the reconstruction of that line is actually really good. So the models, I can't quantify this exactly for this specific feature, but we did check. And then there are other sort of validation checks you can do on the super resolution model, for instance. These two lines here, the heights of these, or the integral under each of these, needs to actually be the same integral as between these two, just with the flipped thing. So this line here corresponds to this line, and this line corresponds to that line. And you can see the ratios between these, we measure them to be actually the same. So here we can see it. We can see the lines individually, separately from each other, because they're sort of more widely spaced. But the reconstruction has the right properties over here as well. Knowing that these relations exist, again, right, we know this from physical understanding of the atomic transitions that happen here. And so we can make these additional tests in order to validate it, but we haven't imposed any of that here. But it's a very good question. There's no simple answer to this. You have to check.
Okay, so one last question.
It's a quick question. Just you mentioned in one of your slides, like you were training a normalizing flow on the latent space. I was like, you could also enforce a loss so that the latent space is Gaussian distributed. Why do you need to do it in these two steps?
Yeah, if you want to fit on a VAE, reconsider your life choices. That penalty is bad. Like the penalty, well, let's not say it's bad. The penalty is potentially problematic, right? You pay a price for that loss that you that structure that you're imposing, and ask yourself the question: what is that structure actually doing for you? Is requiring that the latent space be Gaussian, right? Is that actually useful for anything? And there are cases in which it sort of doesn't hurt. There are cases in which, like, it prevents mode collapse, for instance. So it sort of prevents, like, it gives you kind of a nice volume for the entire distribution, but doesn't really do that much beside it. And there are examples where you can clearly demonstrate that because of that variational penalty, you get, say, image reconstructions that are too soft. It's not quite expressive enough because you pay a price for sort of optimizing that extra part of the loss function. We have a paper from last year or earlier this year where we've done the standard VAE approach for dynamical systems. And a dynamical system, there's nothing about the dynamical system that says its latents need to be distributed according to a normal distribution. If you try that, it really does damage to the long-term predictability, the long-term sort of rollout of a dynamical system in ways that, like, we forced a sort of an time-invariant representation of that thing. And we have way better long-term rollout. So the main point here is, why bother with a Gaussian distribution if you can have your representations do whatever you want? You can align them across modalities. You can be much more flexible about this. And then, well, then you use a normalizing flow in a low-dimensional space in order, if you need a distribution here that you can easily work with, either for sampling or for evaluating the probability, well, just use a normalizing flow for that.
Let's thank Peter one more time.